Welcome to the lecture on solving nonlinear inequalities. In this set of notes, we're going to learn about how you can find solutions to inequalities involving polynomials or rational expressions that are nonlinear. So they're going to have powers bigger than 1. In the first method that we're going to talk about, called the two-dimensional graphical approach, this is only going to apply when you're working with quadratic inequalities. So you want to see an x squared involved. If you have anything other than an x squared, then this method probably isn't going to be your best solution, best method. So the two-dimensional approach, the way this works, is the first thing you want to do is get a 0 on one side of your inequality. And that's called putting your polynomial into standard form. So in this first example, I already have a 0, so I have this x squared plus 7x plus 12 already written in standard form. Once I have that happening, we're going to take that quadratic and we're going to call it f of x. So we're going to label it as a function. So this becomes f of x equals x squared plus 7x plus 12. Once we have our function, we're going to do a rough sketch of that graph. Usually when we're graphing quadratics, we take the time to find out what the vertex is. In these particular problems, you don't need to go to that accuracy. All we want to do is a very rough sketch, and in order to kind of place this parabola correctly, the only thing we're going to find for sure are the x-intercepts. So that's going to be our next step here. We're going to try and locate what the x-intercepts are. So x-intercepts are going to be where y, or in this case f of x, is equal to 0. So we're just going to put a 0 on this side of our equation. So 0 equals x squared plus 7x plus 12. And in order to solve this, if you get lucky, it'll factor, which this one does. So if I set up my two sets of parentheses, I get x, and 3 times 4 gives me 12, and 3 plus 4 gives me 7. So that's why this factors. So my two solutions are going to be -3 from this factor and -4 from this factor. And remember, these are going to be our x-intercepts. Once you find your x-intercepts, the next thing you're going to do is make a very rough sketch. It doesn't need to be perfectly accurate. It doesn't have to be placed exactly right. All we need to know for sure is the x-intercepts that it passes through. So we're going to take -3 and -4 and put those as dots on our x-axis. So I'm going to have 1, 2, 3, 4. -3 gets a dot, -4 gets a dot, and next thing we want to do is basically just decide which way should my parabola go through these two intercepts. Is it a parabola that points up, or should it be a parabola that points down? The way that you determine that is by looking at the coefficient of your x squared term. Here my coefficient is 1, and if that leading coefficient is positive, then you have a parabola that points up. If that leading coefficient is negative, then you have a parabola that points down. So this needs to be a parabola that points up going through these two intercepts. So it would have to have a rough sketch, something like this. Now I don't know for sure how low this vertex is, but we don't really need to find it out in order to answer our question here. So don't worry about finding where that actual vertex hits. Just do a rough sketch. So here's my graph. Now to finish off the problem, what we want to do is figure out which part of this graph is going to give us our solution. And we determine that by looking at our inequality. We want to know where this parabola is less than 0. So a graph is going to be less than 0 if it lies below the x-axis. So the part of this parabola that's below the x-axis is all of this part right here. When we give our answer, what we want to give is the x values that would give us that part of the graph. And all of these values marked in red correspond to x values right in between -4 and -3. So our solution is going to be -4 up to -3. Now, do I get to include those two endpoints? The answer is no, We're going to use parentheses around them because there was no equal bar in my inequality. So I don't want to actually hit 0, which is what happens at these intercepts. We just want to be between them in order to get this lower part of the parabola. So your solution is -4, -3. Okay, let's try that process again. On our next example, we want to take our quadratic and set it to 0, which this one already is. And now we're going to call this our function. So f of x is going to equal -x squared plus 3x plus 2. Once we have our function, remember we're trying to make a rough sketch of this, and we're going to do our sketch using the x-intercepts. So the next thing we want to locate are those x-intercepts. So we're going to replace this f of x with a 0 and try and solve this equation. Now on this one, if you tried to factor it, it gets really close because you are able to get 2 times 1 to give you +2, and 2 plus 1 gives you +3. Unfortunately, there's a negative in front of that x squared, which makes the signs not work out correctly. So this does not factor. So if you want to find intercepts and you're given a quadratic that doesn't factor, then the alternative is to use that quadratic formula. So that's what we're going to use. And remember, the quadratic formula says if you have a quadratic equation of the form ax squared plus bx plus c, then your x is going to be -b plus or minus the square root of b squared minus 4ac all over 2a. So that's the formula that we are going to apply to this equation. So x equals -b. b here is the 3, so I want -3, plus or minus the square root of b squared, so 3 squared, minus 4 times a, which is -1, times c, which is 2, all over 2 times a, which was -1. Now simplifying this a little bit, in the denominator 2 times -1 is -2. Under the radical, 3 squared is 9. -4 times -1 times +2 is going to be a +8. So this is -3 plus or minus the square root of 17 all over -2. Now these are real numbers. They're not nice numbers. They're going to be decimals, but they are real numbers because we got a positive under that radical. So to figure out the rough size of what these are, you want to use a calculator. So if I do -3 plus the square root of 17, get that answer, and then divide that by -2, one of our decimals here is going to be -0.561. For the minus case, we would want -3 subtract square root of 17, and then get that answer and divide it by -2. So my two decimals are -0.56 and 3.56. So those are my two x-intercepts. So on a graph, in our next step, we want to plot those, and you just need to approximate what they are. So -0.56 is a little bit more than -0.5, and 3.56 is around 3.5. So those are your two x-intercepts. Then when you go to make your sketch of your parabola, remember that all you need to decide is, once you know your x-intercepts, should I draw a parabola that points down or points up? And the way that you determine that is by going back to your original function, your f of x, and looking at that coefficient of x squared. This one was negative. So if you have a negative leading term, that means your parabola needs to point downwards. So I need to draw a parabola that points down and passes through these two intercepts. And again, I don't really know how high this vertex should go. It doesn't matter for the purposes of this problem. All we care about is the direction. Now to figure out the final answer, you want to look at that inequality. where on this graph is this parabola greater than or equal to 0? Well, if you're going to be greater than or equal to 0, then you need to lie above the x-axis. So that's going to correspond to all of these points on the parabola. What x's does that correspond to? That's all the x's between these two intercepts. So your answer should be the x values, and in this problem, that was that negative 0.56 up to 3.56, and this time there was an equal bar on my inequality, so I do get to include these two endpoints, so use brackets. Okay? Alright, on our next example, we're going to do the same process again. Remember, these are quadratic inequalities, so that's why this two-dimensional approach works well. First thing you want to do is get a 0, which this one already has. Then you can call your f of x, this polynomial over here on the left side, so x squared minus 2x plus 3. Next step is to find your x-intercepts by setting 0 equal to your quadratic and trying to solve this. This one looks like it will factor, so if I set up my two sets of parentheses, we need x and x, 3 and 1, and I need the 3 to be minus and the 1 to be plus, so that I'll get a minus 2 in the middle. Now, does that actually work? Double check this. If you try to redistribute here, what you'll notice is you do get that minus 2 in the middle, but negative 3 times positive 1 is a negative 3, not a positive 3. So this actually doesn't factor. So remember what you do if it doesn't factor. You have to use the quadratic formula. So that's what we're going to use. So x equals minus b. Here your b is negative 2, so that becomes positive 2. Plus or minus the square root of b squared, so negative 2 quantity squared, minus 4 times a, which is 1, times c, which is 3, all over 2 times a. So simplifying, in the denominator we get 2. Under the radical we're going to get 4, and minus 4 times 1 times 3 is minus 12. 4 minus 12 is negative 8, all over 2. Now here's where I'm going to stop. We got a negative under that radical, and that means that this is a complex number. It's not a real number. When we're graphing quadratics, you can only graph real numbers, not complex numbers. So what does this mean? What it means is that there are no x-intercepts that we can graph. So when we make our graph, we don't have any points to plot. That doesn't mean we can't do the problem. What we have to remember is this is still a quadratic. If you look back at your function right here, which direction does this quadratic need to point? If you look at that leading coefficient x squared, there's a 1 in front, and because it's a 1, that means this is a parabola that's supposed to point up. So how could I draw a parabola that points up yet never hits the x-axis? Well, it could be something over here, something over here, something over here. I don't really know exactly because I don't know what that vertex is. So I'm just going to draw a generic parabola that lies above that x-axis and points up. Doesn't really matter where you position it, because we can answer our inequality looking back at the original inequality symbol. Where does this parabola lie above the x-axis? That's where this is going to be greater than 0. And if you look at this graph, it's always above the x-axis. So for all of these points, we're always greater than 0. So what do you think we would write for our solution if every point here works? Well, our solution is all real numbers. Every value of x works. So this is kind of one of those special case problems. Okay? Let's try another one, another special case. Here we have x squared minus x plus 5 less than 0. It already has a 0, so we're going to let f of x be x squared minus x plus 5. When we try to find those x-intercepts, we're going to plug in 0 for f of x and solve this quadratic. This does not factor at all, so using that quadratic formula, we would have to do x equals minus b, so minus a negative 1 becomes plus 1, plus or minus b squared, so negative 1 squared, minus 4 times a times c, all over 2 times a. Simplifying, in the denominator we just get 2, and under the radical we're going to get 1 minus 4 times 5 is 20, so under the radical we get negative 19. As soon as you get a negative under that square root, you can stop. That means that there are no x-intercepts because these are not going to be real numbers. They're going to be complex numbers. So when we do our graph, we don't, again, have any points to plot because there are no x-intercepts that we can draw. So you want to go back to your function and decide whether this should be a parabola that points up or points down. The leading coefficient here is a 1, so this is going to point up. So again, just like in the last one, we want a parabola that points up and never hits the x-axis. So in order for that to happen, it's going to have to start above the x-axis and do something like this. And again, I don't really know exactly where it should be. Maybe it's further to the left or further to the right. That doesn't really matter. All we care about is the fact that it's above the x-axis and it never intersects. So now to decide what our solution is, look at your inequality symbol. We want to know, where is this parabola less than 0? So where is this parabola below the x-axis? And in this problem, since the parabola is always above the x-axis, this never happens. Our parabola is never less than 0. So what do you think we would write for our solution here? No solution. This parabola is never going to be negative. Okay? Alright, let's try one last example with this two-dimensional approach. Again, you want to make sure you have a 0 first, which we do here. Once you do, you're going to label f of x equals to your function. And you're going to find your x-intercepts. This doesn't look like it's going to factor, so let's try that quadratic formula. So we're going to set 0 equal to our quadratic, and we're going to do that quadratic formula one more time. So x equals minus b, so that becomes plus 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a times c, all over 2 times a. So in the denominator we get negative 2. Under the radical we're going to get 4. And then I've got 3 negatives here, negative, 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 so this is going to stay minus, and 4 times 4 is 16. So under that radical, 4 minus 16 is a negative 12. Again, that's a negative under the radical, so this is not a real number, so we have no x-intercepts. So on my graph, we don't get to hit that x-axis again, but we have a parabola here. The leading coefficient is a negative 1, which means this needs to point down. So we need to draw a parabola that points down but never intersects the x-axis because we don't have any x-intercepts. So I can't draw a parabola that starts up here. I have to draw a parabola that starts below the x-axis because in order to point down and not hit the x-axis, I have to start below it. So there's my graph in general. Looking at the inequality symbol, we're asked, where is this less than or equal to 0? So where is this parabola below the x-axis? And in this case, all of these points are below the x-axis, so every point works. So what do we write for our final answer? All real numbers. Okay? So that's the two-dimensional approach. It's a fairly quick method to use if you are working with quadratic inequalities. The second approach that we're going to talk about today is called a one-dimensional approach. This approach actually works for quadratics, but it also works very easily for other types of inequalities as well. So it's a little bit more useful sometimes than the two-dimensional approach. So here's how the one-dimensional approach works. The first thing that you're going to do is you're going to take your inequality and you're going to make it into an equation by replacing the inequality with an equal sign. So step 1 is to just set x squared plus 7x plus 12 equal to 0. Step 2, we're going to solve that equation. And again, if you're lucky, it will factor. This one does. We get that x plus 3 times x plus 4. And so our two solutions are -3 and -4. This is exactly the same thing we would have done in the two-dimensional approach. In the two-dimensional approach, we would have taken these two solutions and put them as x-intercepts on a graph. Here's where the one-dimensional approach varies. Instead of graphing these as x-intercepts, we're going to graph them on a one-dimensional number line. So I'm going to put -4 on here and -3. And now what we're going to do is we're going to test the three new intervals that we have here. So these numbers and solutions that we just found kind of break up the number line into three different regions. And we're going to test each region to see what's true. Now when you do your testing, it's easier to test this into the factored form of your inequality. So what I usually like to do is off to the side, I'll write down this quadratic in its factored form, so x plus 3 times x plus 4, and we want to know where this is less than 0. So we're going to pick test points and test them into this inequality. And all we care about is whether the answer is less than 0 or not. So we don't really need to go through all the work of figuring out what number this is. We just need to know, is this positive or is this negative? So for example, if I wanted to test a number in this interval, we just need to pick any nice number that's less than -4. So I could try, for example, -5. So I'm going to take -5 and plug it into each of these factors. I'm not going to actually figure out the number part. I'm just going to figure out whether it's a plus or a minus. So -5 plus 3 would be negative. -5 plus 4 would also be negative. Two negatives multiplied together become positive. Is that less than 0? No. So we're going to write a little false up above that interval, because any number in that interval is always going to give me a positive answer, and that's not what we want. We want to be less than 0, which means negative. Okay, so now what we're going to do is test the middle interval. Pick any nice number between -4 and -3, maybe something like -3.5. So if we take -3.5 and add it to 3, that's going to be negative, but -3.5 plus 4 turns to a positive. A negative times a positive is negative, and that's what we want. We want less than 0, so this is true. In the last interval over here, pick something bigger than -3. I like 0. I usually use 0 if I can. So 0 plus 3 is positive. 0 plus 4 will be positive. A positive times a positive stays positive, and that again is not less than 0, which is what we were looking for, so this is going to be false. So your final answer is going to be any interval where you see a true. So in this problem, that's just this one right here. You want to write that as an interval, so -4 up to -3, and because there were no equal bars, these are going to be open parentheses. And here's my solution. Okay, so the one-dimensional approach uses a number line and tests intervals instead of the two-dimensional approach, which plots x-intercepts and graphs your parabola either pointing up or pointing down. Okay, let's try this one-dimensional approach. First thing you want to do again is change your inequality to an equal sign. So we're just going to make this x squared minus 3x equals 2, and then you're going to want to solve that equation. So I'm going to subtract the 2 over to the left side, and we're going to try and factor this if we can. Unfortunately, the signs aren't going to work for me. I can get a -3 from a negative 2 and a negative 1, but that won't give me a minus 2 on the end. So this doesn't factor, so we're going to have to set x equal to minus b, which becomes plus 3, plus or minus b squared minus 4 times a times c all over 2 times a. So we get 3 plus or minus the square root of 9 plus 8 all over 2. So that's 3 plus or minus square root of 17 all over 2. This was the same problem that we did earlier with those decimals that we got. So it's going to be the same two numbers. So this was negative 0.56 and 3.56. So we're just doing the same inequality, but we're doing it in a one-dimensional approach instead of a two-dimensional approach. So once we've found our solutions, instead of making these x-intercepts, we're going to put them on our number line in order, so negative 0.56 and then 3.56, and we want to test this into our inequality. In this problem, what we can do is try and see where this compares to a 0 instead. Usually that's easier to test. So for example, if we had subtracted 2 over to the left-hand side and gotten a 0 on one side, then all we're going to have to do when we test is decide, is our answer, is our sign greater than or equal to 0? It's easier to compare the signs to 0 than it is to try and plug something into here and compare it to 2. So oftentimes I'll try and get a 0 on one side of my inequality first whenever I'm testing points. So over here on the right side, I'm going to write x squared minus 3x minus 2 greater than or equal to 0. Remember, this didn't factor, so that's why I have to leave it in this standard form. So then when I go to test, we need to pick something over here smaller than negative 0.5. So I could try something like negative 1. If we take negative 1 and we plug it into here, negative 1 squared would be positive 1. Negative 3 times negative 1 becomes positive 3. And when I subtract 2, is this greater than or equal to 0? Well, we're going to get 4 minus 2, which is 2. And yes, that does work. So this is going to be true. If we try something in the middle here, 0 is right in between these. So let's test 0. If I plug in a 0, this x squared goes to 0, this 3x goes to 0, so all we have left is that negative 2, and negative 2 is not greater than or equal to 0, so this is going to be a false interval. For the last interval, we want to try something bigger than 3.56, so maybe 4. 4 squared is 16, minus 3 times 4 is 12, minus 2 is going to give me 4 minus 2 or 2, and that is greater than or equal to 0. So that is also true. So my solution is going to be everything over here and everything over here. As intervals, this interval on the left starts at minus infinity and goes up to negative 0.56. I get to use a bracket because we had an equal bar. And then this interval over here starts at 3.56, again using a bracket, and goes up to infinity. And to show that I want both of these, we use that union symbol in between. So here's our solution. Okay? The next examples on the next page are examples where the one-dimensional approach is sometimes a little easier to use than the two-dimensional approach. On these next examples, all the powers on x are either bigger than 2, like these first two. This would be a 4th degree if I FOILed it out, and this is a cubic. These would be hard to graph on a two-dimensional approach because we don't really know what a 4th degree graph looks like usually, or a cubic. These aren't graphs that we're real familiar with. So if you have powers bigger than 2, then you're always going to want to use a one-dimensional approach. Okay? The other examples down at the bottom are rational functions. We've got these fractions, and again, those would be hard to graph. We're probably not that familiar with how to graph x minus 2 over x plus 1. So again, that's why a one-dimensional approach works best, because then you don't have to worry about what a two-dimensional graph should look like. So if we go back to the top, here we have that 0 on the right-hand side. So the first thing I'm going to do in my one-dimensional approach is set this to 0, make it an equation, and we want to solve this. And in both of these two factors here, these are difference of squares, so they can factor down a little bit further. We would get x minus 3 times x plus 3 and x minus 2 times x plus 2. So my solutions are going to be plus or minus 3 and plus or minus 2. So on my number line, we need to put all of those in order. So negative 3, negative 2, positive 2, positive 3. Over here on the right-hand side, I'm going to recopy this original inequality, but I'm going to put it in its most factored form. So that was all 4 of these factors here. So x minus 3, x plus 3, x minus 2, x plus 2, and we wanted to know where this is greater than 0. If you're greater than 0, you're positive. So we're looking for plus signs in order for this to be true. So now we're going to do our testing. If I test something over here, then I need a number that's less than negative 3. So something like negative 4. Negative 4 minus 3 will be negative. Negative 4 plus 3 will be negative. Negative 4 minus 2 is negative. Negative 4 plus 2 is negative. 4 negatives become positive, which is what we want. So this is true. If we test the next interval, I need something between negative 3 and negative 2, so maybe negative 2.5. Negative 2.5 minus 3 stays negative. Negative 2.5 plus 3 turns positive. Negative 2.5 minus 2 stays negative. Negative 2.5 plus 2 stays negative. So now we only have 3 minus signs, so this is going to stay negative, and that's not what we want. We want greater than 0, so this will be false. In the next interval, 0 lies between these, so let's try 0. 0 minus 3 stays negative. 0 plus 3 stays positive. 0 minus 2 stays negative, and 0 plus 2 becomes positive. So now I have 2 negatives, which become positive, and that's what we want, so this is true. You can see that each time I test a new point, one of my 4 minus signs from the beginning turns to a plus. So each time we progress here, one of these signs is going to change at a time. So if we try something between 2 and 3, like 2.5, 2.5 minus 3 is negative. 2.5 plus 3 is plus. 2.5 minus 2 turns to a positive, and 2.5 plus 2 stays plus. So now we only have one minus sign, so that's going to stay negative, and that's not what we want. So this is going to be false. Finally, the last interval, if we test something like 4, finally this last minus sign, 4 minus 3, turns to positive, and all the rest of these pluses stay plus. So we get a positive, which is what we want. So our final answer is going to be where all the trues are. So that's here, here, and here. So writing out these intervals, the one on the left is minus infinity to negative 3. The one in the middle is negative 2 to 2. The one on the right is 3 to infinity. And I'm using parentheses on each of these endpoints because this was strictly greater than 0. So I didn't get to include any equal bar. So unions in between, and here's our solution. Okay, next example, we want to, for our one-dimensional approach, change our inequality to an equal sign. So I'm going to set this equal to that 0, and then we have to try and solve this. Now normally we don't know how to factor cubics very well, but this cubic has 4 terms, and there is a good strategy to use when you have 4 terms, and that's called grouping. So we're going to group together these two and group together these two and try to pull out a common factor from each of these. So the first two here have an x squared in common. If I factor it out, I'm left with an x plus 2. These two terms over here have a minus and a 4 in common. If I factor it out, I'm going to be left with an x plus 2. This is great because now what's in parentheses matches exactly, so I can pull out that x plus 2, cross these guys off, and what I'm going to be left with is x squared minus 4. Now x squared minus 4 actually is a difference of squares, so that even factors further into an x plus 2 and an x minus 2. So if you wanted to write this in completely factored form, notice that these two factors are the same, so sometimes we would just write this as x plus 2 quantity squared times x minus 2. In terms of our solutions, we're going to get negative 2 from this factor, and we're going to get positive 2 from this factor. So the numbers that we're putting on our number line are negative 2 and positive 2. What we're going to write for our factored form is this one right here. This is our most factored form, and I like leaving that square in there because that's going to help us determine our signs a little quicker. We want to know where this is greater than or equal to 0. And remember, greater than 0 means positive, so we're looking for plus signs. So let's test. If we test over here to the left, we would want to test something smaller than negative 2, like negative 3. Now here's where that square comes in handy. We all know that whenever you square something, it always turns it positive. So no matter what I plug in to this first factor, the answer is always going to be a positive. So don't waste your time plugging something in there, because we know the answer is always plus. So all I have to do is plug it into the second factor. Negative 3 minus 2 is negative. A positive times a negative will be negative, and that's not what we want. So this is false. If I go to the middle interval, I could test something like 0, that's in between. This first factor is always plus because of the square, and 0 minus 2 is still negative. So this one, we get a negative back again. We didn't change signs. So on this particular problem, it didn't alternate true, false, true, false. So be careful. The last interval, pick something bigger than 2, so maybe 3. This first factor is plus, and 3 minus 2 is a plus, so a plus times a plus stays plus, and that's what we want. So that interval is true. So our solution is this inequality on the end, which is going to give me the interval 2 to infinity. We had an equal bar in our inequality, so I get to use a bracket. And here's my solution. Okay? Alright, the next two examples are rational inequalities. They have fractions in them. So here we have to be a little bit more careful when we're using this one-dimensional approach. When you're doing the one-dimensional approach on these fractions, there's two things that you need to do. First, we're going to find out where this equals to 0. So we're just going to replace that inequality with an equal sign. And think about, where does a fraction equal to 0? A fraction is only going to equal 0 when its numerator is 0. So this fraction is only going to equal 0 when x minus 2 is 0. So we are going to solve that and just get x could be 2. So that's going to be one of the numbers that we put on our number line. Because we have a fraction, there are places where x would be bad, and that's going to be where your denominator would be 0. So the denominator equal to 0 would be x plus 1 equals 0. So you need to consider that. And if I subtract 1 here, that's going to give me a second point to put on my number line. So that's going to be negative 1 and positive 2. So when you're dealing with these fractional inequalities, make sure that you find out where the denominator is 0 and where the original inequality, or where the original fraction, is equal to 0. So here that was where the top was 0 and where the bottom was 0. So now that we have these two places where it's 0 or undefined, we're going to put these on our number line in order, negative 1 and 2, and we're going to substitute them in to our inequality, x minus 2 over x plus 1 greater than or equal to 0, and we're going to test just like we did before. So to test over here, we would want to test something less than -1, like -2. Now we're looking for where this is greater than or equal to 0. That's a positive. So I'm going to substitute in -2 up here. -2 minus 2 on top is going to be negative. -2 plus 1 is going to be negative. And a negative divided by a negative is plus. That's what we want. So this is true. If we check the next interval, -1 and 2, 0 lies between there. So 0 minus 2 on top will be negative. 0 plus 1 on bottom becomes plus, and a negative divided by a plus is negative. That's not what we want. So this is going to be false. For the last interval, something bigger than 2, I could try 3. 3 minus 2 is plus. 3 plus 1 is plus, and a plus divided by a plus stays plus, so that's true. So it looks like our solution is going to be here and here. So when you write your interval, it's tempting to just say minus infinity to -1 with a bracket, union 2 to infinity with a bracket, because we had an equal bar. However, there's something a little bit wrong with that solution. Remember that -1 wasn't where this was equal to 0. -1 was actually where this fraction became undefined. So you can actually plug in -1 into this problem because it becomes undefined. So we don't want to include the -1. So I'm going to erase that one bad point and put a parenthesis around it. The 2 is okay because the 2 is where this was equal to 0. But the -1 was where this was undefined, so it doesn't make sense to include it because it won't work if you plug it back in. So here's our final solution. Okay, let's try another one of these. So here we have 4 over y plus 2 less than -2. So what I like to do if I don't have a 0 on one side of my inequality is I usually make it become a 0 by adding that 2 over to the left-hand side. So that's what I'm going to do here. I'm going to take 4 over y plus 2, add that 2 off to the side, and now this inequality becomes where is 4 over y plus 2 less than 0. Now to get the numbers that go on our number line, remember one place you always want to check is where that denominator is going to equal 0. So this denominator is y plus 2, and if I solve for y, that means one of my numbers that I need to put on my number line should be -2. To get the other number or numbers, you're going to change this inequality to an equal sign. And you're going to solve this equation. So to solve this, it's actually easier to just clear out that fraction. So to clear out your fraction, you just multiply through by your denominator, which is y plus 2. So I'm going to multiply y plus 2 times the fraction, times the 2, and times the 0. So if we do y plus 2 times 4 over y plus 2, the y plus 2's cancel out, and we just get 4. In the middle, 2 times y plus 2 just becomes 2 parentheses y plus 2. We'll distribute that in the next step. Nothing canceled out there. And 0 times y plus 2 stays 0. So now we just have to solve this equation. It's a little easier than the original one because there's no more denominators. So let's distribute our 2. Combine like terms. 4 plus 4 is 8. And now getting the 8 to the left or the right side, dividing by 2, I get y could be -4. So the two numbers that we're going to put on our number line are -4 and -2. And what we're testing them into is this inequality with the 0. I like to compare to 0. I think it's a little easier than trying to compare to -2. So we have 4 over y plus 2 plus 2, and we want to know where this is less than 0, which means we're looking for negatives this time. So let's test. If we pick something less than -4, like -5, 4 over -5 plus 2 plus 2, we're trying to see, is that less than 0? Well, 4 over -5 plus 2 becomes 4 over -3, and 4 over -3 plus 2, if you're not sure what that is, remember you can always use a calculator here to help you out, especially on these where the numbers aren't quite as nice. 4 divided by -3 plus 2 gives me 0.667. So that's a positive number, and that's not what we wanted. We wanted a negative. So this is going to be false. If we try -3 between these two to test, then in the denominator, -3 plus 2 is -1. So we get 4 over -1 plus 2. 4 over -1 is -4, and -4 plus 2 is -2. That is less than 0. That is negative. So that's going to work. So this is true. For the last interval, we could test maybe 0. So on the top I get 4, and 0 plus 2 is 2. So 4 divided by 2 is 2. 2 plus 2 is 4, and that is not going to be negative. So this is back to false again. So our final solution is just where the trues were, so right here in the middle. So our solution is going to be -4, -2. Here we didn't have an equal bar at all, so we don't even have to worry about any brackets. Both of these endpoints are going to be parentheses. Okay, so that one's a little bit tougher because you are trying to compare this fraction and you had a -2 involved, so it gets a little bit messy. But if you just go slow, test all of your intervals, use your calculator if you need to, and just try to figure out where this is positive or where this is negative. Okay, for our last example, we're going to look at another rational inequality, which means it has a fraction involved. And in order to do this, remember the first thing that we want to look at is where the denominator could possibly equal to 0. If we have the denominator equaling 0, then that is going to be a trouble spot. This is going to be a place where this fraction becomes undefined, and we don't want that to happen. So the denominator here is x, and where can x be 0? Well, right at 0. So the first point that we're going to be putting on our number line is just going to be x equals to 0. The other places that we want to look at are going to be where the numerator could be equal to 0, because that's what's going to make this equation true if I were to replace this inequality with an equal sign. So if I look at this fraction, 2x minus 3 quantity squared over x, and I want to know where it's true, where it's equal to 0, think about where a fraction equals to 0. A fraction only equals 0 when its numerator equals to 0. So then the question becomes, well, where does 2x minus 3 quantity squared equal to 0? And that's only going to equal 0 when this inside expression becomes 0. And 2x minus 3 equals to 0 if I solve for x at 3/2. So the second number that I want to put on my number line is going to be x equals to 3/2. That's the value of x that makes this inequality true if I were to replace that inequality with an equal sign. And x equals to 0 is going to make that inequality undefined. So let's make our number line. I'm going to put 0 on the left and 3/2 on the right to keep it in numerical order. And now we want to test different points and see what regions of this number line are our true intervals. So let's take, for example, something in this region right here, something less than 0. So let's try -1. So if I take my inequality, which is 2x minus 3 quantity squared all over x, and we want that to be less than or equal to 0. Now remember that less than 0 means negative. So we're trying to make the value on the left-hand side be something that either equals 0 or less than 0. So in this case, if we were to plug in -1 into that numerator, take the help where you can get it here. Remember that square up there in the numerator. You know that anything that gets squared turns positive. So this numerator, no matter what you plug in for x, is always going to have a positive value. So I'm not even going to waste my time plugging anything into that. I know that the numerator is always a plus. If I plug in -1 into that x in the bottom, then that's going to stay -1 in the bottom. So I have a positive divided by a negative, which stays negative, and that is less than or equal to 0 because that's negative, so that works, which means this is a true interval. So now let's pick something in this region right here, something between 0 and 3/2, so we could try 1. Again, using that numerator and the fact that it's a square means the top is always going to be positive no matter what. And if I plug in a positive 1 in the bottom where that x is, then the denominator will also be positive. Positive over positive stays positive, which is not negative, so that means that doesn't work, so this region is going to be false. Finally, we want to test something bigger than 3/2, so maybe something like 2. Again, the numerator of this fraction is always positive because of the square, and if I plug positive 2 into the denominator, then that's going to stay positive. Positive over positive stays positive, which is not negative, and that's not what we want. So this is also going to be false. So it looks like the only true interval that we have here is this one right here, from -infinity up to 0. Now normally when we see an equal bar, we think that we should always use brackets. So we might think that our answer looks like this. But in this problem, that's actually incorrect, because we don't want to include 0 in this example, because where did we get that 0 from? That was the place where the denominator was equal to 0, and that would make this fraction become undefined. So we don't ever want to use 0 as an endpoint, so I'm going to erase this bracket and instead use just a parentheses. That way I'm not ever making that fraction undefined. Now where was this fraction actually equal to 0? That was right at 3/2. Now 3/2 wasn't one of our endpoints in one of our true intervals, but it would make this inequality true because that's going to be the case where this actually equals to 0. So I want to include it as part of my solution. So the way I'm going to show that is I want all of the values of x in this interval, all those places where this was true, but I also want to add to that, and I'm going to use that union symbol to show that I want to add to this solution the number 3/2 as well, because that was where this became equal to 0. Now since that's just a solitary number or a single number, I'm going to use those curly braces to show that set. So my solution is all the values of x less than 0 or 3/2. Okay, the two things that we learned today were how to use one-dimensional analysis and two-dimensional analysis to help solve nonlinear inequalities. When you're doing a two-dimensional analysis, usually we use that only when we're dealing with mainly quadratic functions. One-dimensional analysis can also be used to solve quadratic inequalities, but it's also more powerful in that it can be used for rational inequalities or any kind of inequalities that have higher powers than just a quadratic power. So it's a very powerful tool. Alright, that concludes our lecture on nonlinear inequalities. Good luck.